We've been having a very nice ride talking about polynomial equations. And in this video, we're talking about polynomial greatest common divisor, what some other people call highest common factor, and Euclidean algorithm. So, like these videos have been, it's like we have been rolling over ideas. Like we pick up an idea that we've dealt with before, and then it rolls over into a new concept. So I know before now we've talked about things like factorization that involves the first thing, of course, you look out for in factorizing a polynomial is the greatest common divisor. If that is not there, then you can now begin to talk about other things like maybe you're looking at patterns, like maybe sum of squares or difference of two squares and things like that. Okay, so let's move on and look at this polynomial GCD and Euclidean algorithm. So like I said, GCD is greatest common divisor, right? In this lesson, we study divisibility of polynomials. How do you know that one polynomial can divide another? All right. Two, we want to talk about greatest common divisor of polynomials, which we've, of course, encountered previously. And we look at the Euclidean algorithm and extended Euclidean algorithm for polynomials. So let's dive into it. So let's first of all, divisibility of polynomials. We work in f of x, that's a field, right? The set of all polynomials with coefficients in a field f. For example, f can be all sets of rational numbers or all sets a set of all real numbers or the set of all complex numbers. So we say g of x divides f of x if there exists a polynomial q of x belonging to the field f of x such that f of x is equal to g of x q of x. So we write this as g of x divides f of x. So if no such q of x exists, we write that g of x does not divide f of x. So a unit in the field f of x is any non-zero constant polynomial because it has a multiplicative inverse in f of x. So we are simply saying that g of x divides f of x if we can say that f of x over g of x is equal to a particular d of x. Basically, that's the whole thing we are saying, such that we can now say f of x is g of x multiplied by d of x. So from previous ideas that we talked about before, right? We talked about so this f of x then can be seen as the dividend. So it is what you're dividing. G of x is the divisor. That is what is dividing, what you're using to divide, and d of x is what you call the quotient. And sometimes you have remainders, okay? But we're talking about divisibility. So if there's a remainder, then it means it's not divisible by whatever you're dividing it with. So that's exactly what we are saying right there. So if no such q of x exists, okay, yeah, what I call d of x, I should have called it q of x so that it will follow the name quotient, okay? Quotient q of x. So q of x, okay? That's q of x, like that. That's the quotient. So, um, let's talk about some basic properties of divisibility. Now, let f, g, and h all belong to the set of polynomials with that are not constant. That means, a constant polynomial is a constant number that it's always the same, no matter what the value of x is. But then maybe we have it's at least linear, quadratic, or whatever. Okay, it's not constant. So we can have so in a reflexive case, we can say that f divides f. If f divides f, then it means that q of x is most like q of x is 1, that means the quotient is 1 because they are the same. So if f divides f, then the quotient is 1. F always divides f. That's one property of divisibility. Another property is that units divide everything. So if C belongs to f and C is not equal to 0, then C always divides f because f of x is equal to C times C inverse f of x, like that. So now, because we have said it already that any polynomial we take in f, its inverse is also there. So if its inverse is there, it means that the inverse can cancel out the original thing and then we have our f of x back. So units divide everything for sure. Then what if we also have the idea of transitivity. So if G divides F and H divides G, it automatically means that H divides F. Okay? So G divides F and H divides G. That means H automatically divides F. So you can see how it goes. G divides F, right? And H divides G. So that simply means that H will have to divide F like that. Okay. Okay. So what G, F, HG, and HF. So that's the idea of transitivity for sure. So it's just more like if 6 divides 24 and 3 divides 6. So that means that 3 divides 24. Basically, that's what we're saying. So if 6 divides 24 and 3 divides 6, it means that 3 divides 24. Basically, that's what transitivity of for divisibility of polynomials is about. Then we have zero polynomial. Every polynomial divides the zero polynomial. So for instance, we have 0, 0 is always equal to f of x times 0. So for f divides 0, so f divides 0 for any x, right? So any for the zero polynomial, I mean the zero polynomial is always divisible by every other polynomial, right? So because the answer will always be 0. So that means you have 0 of x. I mean, or let's say 0 over f of x. That's only 0. That's all we are saying there. So cancellation idea or which is the informal now. So if A divides BC and A is co-prime with B, then A divides C, right? So if A divides B times C, okay, and A is co-prime with B, then A is C. So this is clearer once we define the greatest common divisor and the co-prime, right? So that's what that is about. So let's look at some division algorithms for polynomials. Division algorithm for polynomial. I mean, we've done polynomial division before, but this is us trying to go deeper into some theory about this. So the division algorithm is the main tool behind the Euclidean algorithm. So the theorem for division algorithm, let f of x and g of x belong to the set of all non-constant polynomials with g of x not equal to 0. Then there exists unique polynomials q of x, that's the quotient, and r of x, which is remainder, such that f of x is equal to q of x, g of x times q of x plus r of x, where either r of x can be 0. So if r of x is 0 now, we say that uh, uh, that's when we say that G perfectly divides F because there's no remainder. So, or we say that the degree of R of X is less than the degree of G of X. Then if R of X is 0, then G of X divides F of X, right? If R of X is not equal to 0, then G of X does not divide F of X. So, like, if I need to demonstrate that better from what we've had before. So imagine that you now have, you have f of x. Okay, let me change the marker here. Imagine that you have, um, f of x divided by g of x, and that gives you q of x plus a remainder r of x all over g of x, right? So in this case now, we say that this is the dividend, that is what you are dividing, and then this is g of x, which is the divisor. The divisor is what you are dividing with. Dividend is what you are dividing. Divisor is what you are dividing with. Q of x is the quotient. This is a quotient. That is the answer you get. And r of x is the remainder, okay? R of x is the remainder. I've said this in a video before. So if you multiply through by g of x now, okay, so you have f of x all over g of x equals q of x plus r of x all over g of x all over g of x, because r of x is the remainder here now. Okay, if you multiply through by g of x, you have f of x all over g of x times g of x equals q of x times g of x, okay? Then plus r of x all over g of x times g of x. Okay, we've done this several times. So you see that now this cancels out. So we now have f of x equals g of x multiplied by q of x plus r of x. So you see that the dividend is equal to the divisor multiplied by the quotient plus remainder. So we are now saying that if r of x is equal to 0, then we say that g of x, g divides f. That means g goes perfectly in f. But if r of x is not equal to 0, then we say g doesn't divide f, okay? Because there's a remainder. So, and we see that playing out in the remainder theorem and the factor theorem that we had done previously. Okay. Uh, So we have that. So we have divisibility now. Okay, now I think there's a very important point here. So when you have this expression, either r of x is 0, that is, there's no remainder, or if there's remainder, it means that the degree of r of x is less than the degree of g of x. I think that's a very important factor to consider. So the degree of r of x, okay? So because of what we have here, because of this expression now, it is important that the degree of r of x will always be less than the degree of g of x. Okay, because after dividing, they cannot have, if they have the same degree, it means you still have some division to do. Okay, so if this one has power 0, this one should have power 1 at least. If this has power 1, this one should have power 2 at least, or more. If this one has power 3, this one should have power 3, I mean power 4 at least, like that. So the degree of r of, so it's either there's no remainder, or if there's remainder, the degree of the remainder is less than the degree of the divisor. That's the way to guarantee that you have done a thorough job of dividing. Okay, so let's go ahead and talk about an example of divisibility. Okay, so let's go step by step. Example 1 on divisibility. So does g of x, which is x minus 2, divide f of x, which is x cubed minus 3x squared plus 4, over the real number? So we can use the factor theorem. So for factor theorem, we want to see if x minus 2 divides f of x. So, and we know f of x minus 2 divides f of x if and only if f of 2 is equal to 0. That is, if you equate x minus 2 to 0, you get x equals 2. So if you put 2 into this expression and you get 0, then that means that f of x is divisible by x minus 2. So let's do that. So you have 2 raised to power 3 minus 3 times 2 squared plus 4. So that's 2 raised to power 3, 8. 3 times 4, 12, then plus 4. So 8 plus 4 is 12. 12 minus 12 is 0. So since f of 2 is 0, we conclude that x minus 2 divides f of x. We've done this plenty times. So to find the quotient, we can then perform polynomial division. So there are different ways to perform polynomial division. You can use the synthetic method, or you can also use the synthetic method, or you can use long division. So I'm going to do the 2 again. I've done this before. So now we have established that, okay, well, let me just go ahead. Thus, so the question is, does g of x, which is equal to x minus 2, does it divide f of x, which is x cubed minus 3x squared plus 4 over r of x? So that's the question, right? So let's deal with that now. So again, does g of x equal x minus 2 divide f of x, which is x cubed minus 3x squared plus 4? That's the question. So, I mean, to do that, we need to go through the steps. So we know from the factor theorem, okay, from the factor theorem, g of x, which is equal to x minus 2, divides f of x if f of 2 is equal to 0. So we need to check if that is true. So now f of 2 is 2 raised to power 3 based on the expression, minus 3 into 2 squared, 3 into 2 squared, all right, plus 4. So we have 2 raised to power 3, which is 8, minus 2 raised to power 2, 4 times 3, that's 12, then plus 4. Then everything is equal to 0. So, and that's why we say, since f of 2 is equal to 0, then g of x, which is equal to x minus 2, actually divides f of x like that. So the next question is to find the quotient, okay? So to find the quotient, that's our q of x now. To find the quotient, so what we then do is we can use long division. Okay, we can use long division, and then we can also use what is called synthetic division. I have a whole video made on this already on polynomial division. So we have all of this long division or polynomial division. So I'm going to use the two. So let's start with long division. Long division. Okay. So for long division, we have, so what you do is this. Any, so you have x squared minus 3x squared plus 4. But there's a problem here. Okay, sorry, I did that wrongly. This should be x cubed minus 3x squared plus 4. You have that here, and then you have x minus 2. But there's a problem here. When you want to, anytime you want to do either synthetic or long division, every coefficient of every term every term in x has to be there. Now we have power 3, power 2. There's no power 1, but we have power 0 because 4 is power 0. So anyone that doesn't exist, you have to put it by adding 0, x raised power 1 plus 4. Now x raised power 0. X raised power 0 is 1, so we can leave that out. And you have x minus 2 here. So this is how you set up long division. So if you don't do that, you're going to have a bit of confusion in doing the division. So very important to pay attention to this. So now that you have set this up, what are you going to do? You take this x and you say the x, when x divide x cubed, what do you get? You get x squared. So x squared times x gives you x cubed. Then x squared times minus 2, that's minus 2x squared. So once you've done this, you can then subtract. So when you subtract this, you have x cubed minus x cubed, 0. Now, minus 3x squared minus minus 2x squared. That's minus 3 plus 2, which is minus x squared. Now, you see the reason why you have to put the coefficient of x, which wasn't there, at 0, because you now need to bring that down here. So, next step now, you then say this x now in x squared. So when x squared divides minus x squared, you have minus x. So minus x times x, you get minus x squared. Then minus x times minus 2, that's plus 2x. So you see the usefulness of this 0x now. Then you can continue. Minus x squared, so you subtract now. Minus x squared minus minus x squared, that's minus x plus x, minus x squared plus x squared, which is 0. Then 0 minus 2x, that will give you minus 2x. And then you can drop the 4 now, that 4. Then you go again. So when x divides minus 2x, so when x divides minus 2x, you have, x divides minus 2x, you get minus 2 because minus 2x over x is minus 2. So minus 2 times x, you have minus 2x. Then minus 2 times plus, minus 2 times minus 2, you have 4. So then you subtract. When you subtract minus 2x, 0, 4 minus 4, 0. So all this is gone. So there's no remainder. So that means there's no remainder. You can then say, so, all right, so f of x, which is all over g of x, is the same thing as, what's that f of x? Now f of x is x cubed minus 3x squared plus 4 all over x minus 2. Okay, and that is equal to the quotient, which is minus 2x plus 4, easily. Okay, so that, oh, sorry, that's x squared minus x minus 2. X squared minus x minus 2. So you have x squared minus x minus 2. So you can then write this whole thing as this x cubed minus 3x squared plus 4 equals x minus 2 into x squared minus x minus 2. Now, this is a quadratic expression which you can factorize further. But, I mean, that's probably not the question we are answering. We have seen, so we can then conclude, right? We have concluded already that g of x, can divide f of x. And we have gone further to do something extra to find the quotient, which we're not required to do in the first place. So, I mean, this whole thing is explaining how the long division is done. So this may look really clumsy, this may look clumsy. So I won't even bother myself because what I've done already is the easier way to do it. But then that's not even the easiest of ways to do it. This is long division now. What if we go for synthetic division? So this is the approach of long division. So what about synthetic division? Okay, so for synthetic division, let me change this. So synthetic division, okay? So for synthetic division, again, don't forget, we have f of x equals x cubed minus 3x squared plus 4, while g of x is equal to x minus 2. So to use synthetic division, what do we do? So see what you do. Again, you have to make sure this is complete. This has all the terms. This is x cubed minus 3x squared plus 0x plus 4 because all the terms in x must be there. Okay? So to set up synthetic division, it is done beautifully this way. So for f of x now, so you have f of x somewhere around here. So all the coefficients of f of x, you have for power 3, you have x cubed, you have 1. For x squared, you have minus 3. For x, you have 0. And for the constant, I like to put this like this because if there's a remainder, you're going to find that around here. Okay? That's the f of x area of things now. And then you have the g of x part here. So for g of x, especially if you equate g of x to 0, so when g of x, okay, I guess I want to use another marker for this. So when g of x is equated to 0, that implies that x minus 2 is 0. That means that x is equal to 2. So this 2 now is what you need. So you can now put this 2 here. Okay, you put this 2 here for x. Okay, now that this is there, you can then have, so then we can now start. We are doing, this is the setup for synthetic division. So how does the synthetic division start? First, you have, so this one now, you drop it, that's 1. So when you drop the 1, you now multiply, you say 2 times 1, that'll be 2. Okay, so minus 3 plus 2 is minus 1. So next, go again. This 2 now multiply by minus 1. So 2 times minus 1, that's minus 2. So 0 minus 2 is minus 2. Okay. Next, you go again and do this. 2 times minus 2. That's minus 4 down here. So 4 minus 4, not times, just add. 4 minus 4, you have 0. So this 0 tells you that f of x is actually divisible by g of x, right? I mean, we've established that divisibility. So this 0 shows you it is divisible. And then, so this shows G divides F. That's a very simple way to state that. And then this 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 are the coefficients. These are the coefficients. These are the coefficients of the quotient, right? These are the coefficients of the quotient. So now from here now to get the quotient, all you just need to do is to put x raised power 0, x raised power 1, x raised power 2. Okay? So we can say that, so the quotient q of x. The quotient is q of x equals, so we have 1x squared, that's x squared, 1 times minus 1 times x. Oh, sorry, this is x raised power 1. Yeah, this is x raised power 1. So minus x, and then lastly, minus 2. Okay, so x squared minus x minus 2. Just exactly the same thing we got, x squared minus x minus 2. So it's the same quotient. So again, we can then say that so therefore f of x over g of x is equal to, that's x cubed minus 3x squared plus 4 all over x minus 2 is equal to x squared minus x minus 2, no remainder. So that implies that x cubed minus 3x squared plus 4 is equal to x minus 2 into x squared minus x minus 2. So because this is also quadratic, we can factorize further. But all we need to know is that the remainder is 0. And from synthetic division, the fact that the last value here is 0 means that G actually divides F and there's no remainder. And that's all we just want to know, is that G actually divides F, and that has been established. And the quotient is x squared minus x minus 2, like we found. So, I mean, if you like, you want to go through this, but I feel this is a more tedious way to do it. So setting up the long division table or the synthetic division table helps you to take care of this better. Okay, we move on to greatest common divisor of polynomials. So let f of x and g of x belong to the set of all non-constant polynomials, not both 0. F of x is not 0, g of x is also not 0. Okay, so a polynomial d of x is called the greatest common divisor, GCD, of f and g if d of x divides f of x and d of x also divides g of x. So d is a common divisor. So if you can find a particular polynomial that divides both f and g, then you can say that is their greatest common divisor. So for any other common divisor, h of x of f and g, we have that h of x divides d of x. So if you have a particular polynomial that divides f of x and g of x, and then any other polynomial you find perfectly divides that d of x. So we say that that d of x is the greatest common divisor. It's like the idea of highest common factor, right? So we write d of x is always the GCD of f and g. So it is the biggest polynomial, so to speak, that can divide the polynomials f and g. Then we have the idea of uniqueness up to constant. So in f of x, where f is a field now, it's a field of non-constant polynomials. So where f is a field, the GCD is unique up to a non-zero constant factor, right? So if d of x is a GCD and c belongs to f with c not zero, then cd of x is also a GCD, right? So cd of x is also a GCD. So that is, if you multiply c by d, automatically it will also be a GCD of the polynomial, of the two polynomials. So to make the GCD unique, we usually choose the GCD to be monic, that is with leading coefficient 1. So if you want a unique a greatest common divisor for a polynomial, you have to make sure that it is monic, meaning that the leading coefficient is 1. So in this lesson, whenever we write GCD f of g, we mean the monic GCD. So let's look at the basic properties, or the basic properties of greatest common divisor. So let f and g belong to f of x, not both 0. That is, f and g are not 0. And f of x, we are talking about non-constant polynomials. And let d of x be the greatest common divisor of f and g, which is monic. Let that be monic. So we have symmetry, meaning that the GCD of f and g is the GCD of g and f. So anyhow you go, it's the same. Then scaling now, for any non-zero constant c, which is also an element of f, then the GCD of cf, g is the same as the GCD of f, g up to a non-zero constant. So with the monic convention, they are exactly the same. Then we also have the zero case. If g is equal to 0 and f is not equal to 0, then the GCD of f, 0 is the monic version of f. If f is 0 and g is not equal to 0, then the GCD of 0, g is the monic version of g, basically, right? So that's the monic thing there. Then we have co-prime polynomials. If the GCD of f and g is 1, okay, that is that you can't find any polynomial that divides the two apart from the constant one. We say that f and g are co-prime or relatively prime. For instance, 2 and 3. If you are talking about numbers, not polynomials now, it means 2 and 3 are co-prime, meaning that there's no number that can divide both of them. So 2 and 3, nothing divides them apart from 1. So co-primes or relatively primes are numbers that can only be divisible by 1, right? So 2 and 3, for instance, are co-prime. 3 and 5 are co-prime. 2, 3, 5 are co-prime because they can only be divided by 1. Then we have the Bézout identity. So the Bézout identity tells us still something more about this. Okay. So for the Bézout identity, the theorem, the Bézout theorem, let f of g belonging to f of x not both 0. Don't forget f of x is the set of all non-constant polynomials. That is a polynomial that is at least linear, right? So f of g belonging to f of x not both 0, and let d of x be the GCD of f and g, be monic. Then there exist polynomials a of x, b of x belonging to f of x such that the that divisor, that d of x, which is the greatest common divisor, is actually a of x multiplied by f of x. So this a of x multiplied by f of x plus b of x multiplied by g of x. In particular, we say that f and g are co-prime, that is, the GCD of f and g is equal to 1. If and only if there exists ax and bx such that 1 is equal to ax times f of x plus bx times g of x. So these polynomials ax and b of x can be found by the extended Euclidean algorithm, which we are going to consider next, right? Okay. So let's look at this now. Let's look at GCD by factoring. You have f of x equals x cubed minus x. So g of x is simply x squared. If g of x is x squared minus 1 over rx now. So we can factor both polynomials. If you factor both, you have f of x is x cubed minus x. That's x into x squared minus 1, which is x into x minus 1, x plus 1. G of x is x squared minus 1, which is x minus 1, x plus 1. So if you take the product of common irreducible factors or the monics, you see that the common factors are x minus 1 and x plus 1. As you can see here, x minus 1, x plus 1 is common to both. So the GCD of f and g now, you can say that will be x minus 1 into x plus 1, which is x squared minus 1. Factoring is not always easy. So we need a systematic method, which is the Euclidean algorithm. So in this case, we could factor very easily. And we see that this is x times x minus 1 times x plus 1. So, I mean, a better way to demonstrate it is you have x squared, x cubed minus x and x squared minus 1, right? So um, you have x cubed minus x, which is x into x squared minus 1. And that is equal to, okay, let me bring it down. So that is equal to x into x minus 1, x plus 1. On the other hand, we have x squared minus 1, which is simply x minus 1, x plus 1. Okay, so the GCD of x cubed minus x and x squared minus 1 is simply, pick this out. X minus 1 is common to both. Pick whatever is common. So you have x minus 1 multiplied by x plus 1 is also common. So you have x plus 1. So that's one sweet way of taking care of highest common factors of greatest common divisors. So x minus 1, x plus 1. So that's what this is about. But this is not always easy. And that's why we need the extended Euclidean algorithm that we are going to talk about next. So Euclidean algorithm for that's why we need the Euclidean algorithm, by the way. So Euclidean algorithm for polynomials is the next one to consider. So the Euclidean algorithm for polynomials works similarly to the integer case. So to find the GCD of f and g with f and g belonging to f of x and not both 0, we want to ensure that the degree of f is greater than or equal to the degree of g. You can swap if needed. So if g comes first, it doesn't matter. So we can divide f by g. So if you divide f by g now, so it means we have f divided by g gives us the q1 plus a remainder, where the degree of the remainder is always less than the degree of the divisor. Very important, something we've talked about before. So you have f equals g q1 plus r1. Q1 is the quotient while r1 is the remainder. If r1 is equal to 0, that is, this remainder is 0, then a monic version of g is the GCD. So if r1 can be 0, then a monic version of g. Of course, the monic version means that that's the version where the leading coefficient, that is the coefficient of the x with the highest exponent, is equal to 1. Then if r1 is not equal to 0, then we can repeat with g of r1. So g and r1. So in this case, we now have g equals r1 q2 plus r2. Okay, and the degree of r2 has to be less than the degree of r1, because here r1 is whatever you're dividing with, the degree has to be the degree has to be bigger than the degree of the remainder. Okay, and if you continue that, you discover that you keep having r1 is now r2q3 plus r3 and so on and so forth. So then when a remainder becomes 0, then the last non-zero remainder made monic is GCD of f and g. Okay, so but degree strictly decrease, so this process stops after finitely many steps. Okay, so let's demonstrate that with the problem we solved not just before we got here. Okay, simple Euclidean algorithm computes GCD of f and g for f of x equals x cubed minus 1 and f of g of x is x squared minus 1. Now, these ones are factorizable, so we can easily factor them out and get it. But using Euclidean algorithm, let's see how it goes. So first of all, we have that f is of degree 3 and g is of degree 2. That based on the exponents. So we divide f by g. So we can divide f by g. We divide by the smaller one. Okay. So divide x squared by minus x by x squared minus 1. So leading term is x cubed over x squared. So x cubed over x squared is x. Okay, so we divide x into x squared minus 1. That'll be x cubed minus x, and so finally, you now have x cubed minus x cubed minus x equals 0. So x cubed minus x is now x squared minus 1 times x plus 0. So the remainder is 0. So we conclude that the GCD of x cubed minus x squared minus 1 is x squared minus 1. And it is monic already. So the coefficient of x squared is 1. Now, I know that may sound like gibberish to you. So because long division is better done using the division table. So let's go for that. So you can get clarity. So we are looking for the GCD of x cubed minus x and x squared minus 1. So the Euclidean algorithm way to do that is to do long division. Now, we can't do synthetic division in this case because synthetic division only happens if the divisor is linear, right? But in this case, if you want to find the GCD in this case now, you have the bigger one, which is x cubed, the one with the higher degree. That's x cubed. That there's no x squared, so you have to put 0x squared. Then you have minus x. We have x cubed minus x. So x cubed plus 0x squared minus x plus 0, which is the constant now. So you have to take care of all of that. And coming here now, for x squared minus 1, in fact, even that, so I think it's safer to have x squared, all right, plus 0x minus 1. Very important. So you are dividing by the one with the with the smaller degree, okay? So now let's go. X squared divided by x cubed. X squared divides x cubed and you get x. Or we are saying x cubed divided by x squared, that's x. So x times x squared, that gives you x cubed. Then x times 0x. You see why we also need this? X times 0x, that is 0x squared. Okay, so we can subtract now. Okay, of course, and x times minus 1, that's minus x here. So we can subtract. So x cubed minus x cubed gone. 0x squared times minus 0x squared gone. Then minus x plus minus x minus x, that's minus x plus x. That is also 0. So I mean, everything is gone. Basically, everything is gone. So we see here that x cubed minus x all over x squared minus 1 simply gives us x. You can see that. Mhm. So in this case now, and there's no remainder, right? There's no remainder. So everything is 0, 0, 0. So no remainder. No remainder. And because there's no remainder like that, so it means that x cubed minus x all over x squared minus 1. We already know this to be true because we can easily factorize this. But we're only talking about a case where you can't easily factorize. So it means x cubed minus x is simply x into x squared minus 1. So we can now take this we can take this as the GCD of both. Okay, this is simply the GCD. So and it is monic already because there's no remainder. So the monic version of this, but it is already monic. So GCD of x cubed minus x and x squared minus 1 is simply x squared minus 1. So because there's no remainder, we would have taken the monic version of this, but the monic version, it's already in the monic version. So we just stop with that. Okay. So, and now we see that's already in the monic form. So what I've gone to do on the other page is the long division, which is easier done when you see the table, how it's progressing than all this story version. Okay. Now let's do another direct division. So imagine you have GCD of f of g. You want to find the GCD compute GCD f of g for f comma g for f of x is x cubed minus 2x squared minus x plus 2. So g of x is x squared minus 1 again. So over q of x or r of x, that's rational or real numbers. So divide f by g because the one with the lower power, that's what you divide by. So you want to you divide f by g. Okay, so the dividend is f now, the divisor is g of x. So if you divide all that, you end up getting that the GCD is also x squared minus 1. Well, I mean, just like I said, I always like to do the division using using that setup that you can easily follow. So you have x cubed minus 2x squared minus x plus 2, and then you have x squared minus 1 again. So you want to find the GCD of that. So let's go again. So find the GCD of f of x equals x cubed minus 2x squared minus x plus 2, okay, and g of x, which is equal to x squared minus 1. What do? Again, you go for the setup. So we have this, which is x cubed minus 2x squared minus x plus 1. So you can see all the terms are there, power 3, power 2, power 0, power 1, power 0. And then we are divided by x squared minus 1. So you have x squared. There's x squared minus 1. There's no power 1. So you have plus 0x minus 1. So what do? X cubed divided by x squared, that's x. So x times x squared, that's x cubed. X times 0x, that's 0x. X times minus 1, that's minus x. and then you subtract. So if you subtract here, you have you have 0, and this is 2x squared, right? Minus 2, oh, sorry, minus 2 minus 0, that's minus 2x squared. Then minus x plus x, that is 0x, very important. And then you can bring down plus 1. So we go again, and we have minus 2x squared divided by x, that's minus 2, okay? That's minus 2. So minus 2 times x squared, that's minus 2x squared. Minus 2 times 0x, that is 0x, 0x. So that's plus 0x. Minus 2 times minus 1, that's plus. Minus 2 times minus 2 times minus 1, that's plus 2. Okay? So when you divide, okay, you have this is 0, this is 0. So you subtract rather 0, 0, and this is minus 1. So we have a remainder of minus 1 here. Okay, 1 minus 2, that's minus 1. So you can then say, so g of f of x all over g of x, which is the same thing as x cubed minus 2x squared minus x plus 2 all over x squared minus 1, is the same thing as what you got up there, which is x minus 2. So um that's x minus 2 plus the remainder, uh, say minus 1 all over x squared minus 1. So you see, though there's a remainder here, but at least we have a division happening right there. Okay. So so it means that whatever we have is actually the greatest common divisor, right? So this means the x squared minus 1 we have is the greatest common divisor. So of course you can divide it by multiply it by x squared minus 1 here. So you have x cubed minus 2x squared minus x plus 2 is equal to x minus x squared minus 1 into x minus 2, then minus 1, which is the remainder. So this is the expression you have. So you see here, so from this story division we have here, I think, what do we have? Okay, there's no remainder. What did I do wrong? This is plus 2. Okay, I guess I did. There's a mistake. There's a It's plus 2, sorry. This is plus 2. My bad. This is plus 2. This is plus 2 actually. So this is plus 2. So this is 0. Okay, sorry. This is 0. So there's really no remainder. So this is gone. So no remainder. Yeah. Okay. So no remainder. So even if there was a remainder, it's still the same thing, that this is the GCD. This is the GCD. Okay. So we can say that, so GCD of f comma g is still x squared minus 1, because the only difference is that if there's remainder, then we use it that way. But if there's no remainder, that means that we have to take the monic form of the divisor. But I mean, it's already in the monic form, so we have that. So yeah, this is plus 2. So I wonder why I wrote plus 1 in the first case. All right. So that goes. Then we come again here. So after all the division, right, you see this, you now see that the GCD of this and this is x squared minus 1. Okay. So let's look at a multi-step algorithm for the same thing. Okay. So imagine that you now have, I mean, for division, right? We're talking about greatest common divisors and Euclidean algorithm. Looking at a multi-step algorithm now. So first of all, you want to compute the GCD of f comma g for x cubed minus x plus 1 and x squared minus 1. So first of all, divide f by g. So divide by the one with the smaller degree. That's the usual thing to do. So when you do that, we've done that a couple of times. So I'll just follow this one now. So the leading term is x cubed minus x, then over x squared, you get x. That's x cubed minus x squared, you get x. Then multiply now. So you have this x times x squared minus 1. You have x cubed minus x. So then you can subtract now. So you have x cubed minus x plus 1 minus x cubed minus 1. So x cubed cancels minus x cubed, minus x plus x gone. Then you have 1 minus nothing, that's 1. So that's the remainder now. So we now see that x cubed minus x plus 1 is equal to the divisor, x squared minus 1 times the only thing you've got so far is x plus 1. So in this case now, you can say that f is g times x. So g multiplied by x plus the remainder, the first remainder. And the first remainder is simply 1. Okay, now that you have got the remainder to be 1, then you go for the next step, you now do the next division step. So you now want to find the GCD of G and R1. So you've done G and F and G. So the next thing you want to do is G and F. So I mean G and R1 that you got, but R1 is already a constant. So I mean that makes life easy. So the GCD of x squared minus 1 and 1. Well, how do you divide? You have x squared minus 1 divided by 1. You end up getting the same thing. So you have x squared minus 1 is 1 into x minus 1 plus 0. So the last non-zero remainder is 1. Therefore, the GCD of x squared minus x plus 1 and x squared minus 1 is equal to 1, like that. So that's the greatest common divisor. So you keep going until you get that last one. So you can see that in this case now, f and g are co-prime. So they don't have anything that divides both of them. So they are co-prime. So and since they are co-prime, then the divisor is simply 1, right? So let's talk about the extended Euclidean algorithm. Let me see. I hope there's a question later that I can solve to drive home that idea. Um, okay, let me see. Okay, maybe I can try question 3. I can try question 3 to see what happens. Okay, or better still. Let's keep going. Let's go. When we get there, I'll know what to do. Let me not worry about that time. I always get ahead of myself. That's the challenge I have, right? So extended Euclidean algorithm. The extended Euclidean algorithm not only finds GCD of f and g, but also polynomials a of x and b of x, such that GCD of f comma g is ax multiplied by fx plus b of x g of x. So this gives a concrete Bézout identity and is very useful when solving polynomial Diophantine equations and working with inverses modulo a polynomial encoding theory or cryptography. So let's look at extended Euclidean algorithm. Imagine that you have f of x equals x squared plus 1 and g of x is x cubed minus 1. So we'll show that the GCD of f comma g is 1 and find a of x, b of x such that 1 is equal to ax into x squared plus 1 and bx into x cubed minus x, right? So first of all, the step 1, you perform Euclidean algorithm and record equations. So first of all, you divide g of x by f of x. So that's x cubed minus x divided by x squared plus 1 because you divide x cubed minus x by x squared plus 1. You divide the bigger degree with the smaller degree. So the leading terms, okay, well, I mean, let me just go and do that because this story thing may just be, you may be wondering what's happening. So x cubed minus x squared plus 1, okay? X cubed minus x cubed minus x, then x squared plus 1. Now, this is not in the best way if you want to really do long division. So if you want to really do long division, you have x cubed plus 0x squared minus x plus 0, which is the constant. And for this too, you have x squared plus 0x plus 1. This is when you can really do something reliable. And you cannot use synthetic division because this is not a linear expression. So synthetic divisions work for linear expressions basically when the divisor is linear. So x cubed divided by x squared, that's x times x squared, that's x cubed, then x times 0x, that's 0x squared, x times 1, that's plus x. Then you subtract. Okay, so x cubed minus x squared is gone, 0x squared minus 0x squared gone, minus x minus x, that's minus 2x. Then you can bring down this 0 now. Then you go again, minus 2x divided by x squared. It's not possible, right? X squared cannot divide minus 2x. So what we have here now is this. We have that x cubed minus x all over x squared plus 1 is simply what did we get up there? That's x, okay? X minus 2x all over x squared plus 1. So it means that x cubed minus x is equal to the divisor, that's x squared plus 1, multiplied by x minus 2x, So this is the remainder right here. So we only get x, and then we have a remainder of minus 2x. So that's exactly what we have right here. So the next thing now is you again you divide f of x by r1 of x. So if you okay, let's see that through. So you now want to divide x squared by this one. So again, you have so we have our first remainder and you keep going. So when you divide this, we have another remainder. So finally, we divide R1 by R2 and we get something. So the last non-zero remainder is GCD. So that means they are co-prime. Okay, I mean, let's keep going so you can get the full picture. So now the deal is we want to find GCD. We want to find GCD of uh x squared plus 1 and x cubed minus 1. That's why we started. So in this case now, we have this first one now. We divide by the smaller power, which we have done, and we got this expression right here. So so we have a remainder R1. Our remainder R1 is minus 2x. As you can see from here, that's our first remainder R1. So now that we have remainder R1, what do we do next? So, you know, um, this is our f of x, right? And this is g of x, and we've divided. So now we have remainder R1. So again, we now want to find the GCD of of g, which we divided with. Okay. That is x squared plus 1, g and R1. So that is we want to find the GCD, want to find the GCD of x squared plus 1. GCD of x squared plus 1, and that's x squared plus 1, and now minus 2x. That's what we want to find. And what do we do again? We do another long division. So we now divide the smaller degree is minus, the one with smaller degree is minus 2x, and the higher degree is x squared. So we have x squared plus 0x plus 1. And for this now, it's simply, okay, we need to pay attention to the constant. So that's minus 2x plus 0. Literally, what you have here, this expression here, minus 2x plus 0. So we go again. So um x squared divided by minus 2x, that's like minus half x. Does that make sense to you? So that's, you have x squared all over minus 2x. X cancels one of these. So you have minus half x, minus half x. Very important. So you have minus half x. So minus half x times minus 2x, that will be x squared, right? Because minus half times 2 is 1. X times x is x squared. Minus half x times 0, we have 0x. Minus half, okay, yeah. So minus half x times 0 is 0. Yeah, minus half x times this is x squared. Minus half x times 0 is 0x. Okay, so we can subtract now. So this will be gone, and we just have 1 here, right? So the last remainder again is 1. So because minus 2x cannot divide again. So what do we have? What we have x squared plus 1 all over minus 2x is equal to 1. Okay? Is equal to, so yeah, is equal to minus half x, sorry. Is equal to minus half x plus 1 all over minus 2x. So if we multiply through, we have x squared plus 1 is equal to minus 2x into minus half x minus uh minus 1, right? Yeah, plus 1. Sorry, not minus 1, plus 1. So we have this now. So you see here, the remainder we had here was minus 2x. So now we have R2. So this is now R2. This is R2. The first remainder was minus 2x, which is R1. Like this one is R1. So now we now need to compare R1 and R2. So we have R1, R2, which is equal to, so what R1 is minus 2x and R2 is 1. Okay? R2 is 1. So the GCD of R1, R2, we don't need to do long division now. Uh, Minus 2x and 1 are co-prime. So the GCD is simply 1 because only 1 can divide them. So what that simply means is that because at the end of the day, the last remainder is 1. So we can say that, so what we started with, so you see it's a long journey we're coming from. So x squared plus 1, x cubed minus 1. So GCD of x squared plus 1, x cubed, x squared plus 1, right? X squared plus 1 and x cubed minus x. Sorry, this is x cubed minus x. So x cubed minus x is 1. So f of x equals x squared plus 1 and g of x equals x cubed minus 1 are co-prime because their greatest common divisor is 1. So they are co-prime. Nothing else divides them apart from 1. That's what it means for something, for two polynomials to be co-prime. So the last non-zero remainder is 1. Um, so GCD of f and g is equal to 1. So by backward substitution now, we can then say to find a of x and b of x. So from x squared plus 1, from x squared plus 1, we had this minus 2x plus minus half x plus 1. So that's we also got that here, right? Here. So this expression, okay, I think it makes sense if it's another marker. So we have this expression minus 2x minus half x plus 1. So we now take it backwards. So we have minus 2x into minus 1 over 2x plus 1. So we rearrange to isolate 1. So if you isolate 1 now, we have, so we now have 1 to isolate 1. So we have x squared plus 1 equals minus 2x. So we have minus 2x into minus half x. So what we have done here is we transfer everything. So you have x squared plus 1 minus, so everything here minus 2x into minus 1 over 2x. We also have from the first division step that x cubed minus x is x squared plus 1 times x plus minus 2x, which was the first remainder. So now we have minus 2x again. We isolate the minus 2x. So minus 2x again becomes x cubed minus x. Then you transfer this whole thing. That's minus x squared plus 1 times x. So we substitute this expression for minus 2x into the formula for 1. So we have so, from the formula for 1, we had minus 2x right here, right? So we had minus 2x. So we now have x squared plus 1 plus half x into x cubed minus 1. So because minus 2x is this whole thing now, so we put, for this expression now, you have this minus half x right here. So minus 2x alone now is this x cubed minus x minus x squared plus 1 into x. So you put the whole of that. So if you group the like terms, f of x, so you see that f of x is x squared plus 1 and g of x is x cubed minus 3. So if you group the like terms, you end up having the terms with f of x. So x squared plus 1 minus half x squared into x squared plus 1 is now 1 minus half x squared into x plus 1. So, and the term with g of x now. So you see the term with f of x is x squared plus 1. So this right here. So the term with f of x, you have this part. That's x squared plus 1 minus half x squared into x squared plus 1. Then the term with g of x being x cubed minus 1. Oh, sorry, the term with f of x squared plus 1. So you take this x plus 1 into, yeah, you have x plus 1 first, and you take minus half x into x squared plus 1. You have this now. So x squared into x squared plus 1. So you tidy up, when you tidy all of that up, you have 1 minus half x squared into x squared plus 1. And the term with g of x, which is x cubed minus x, this part now, that's half x into x cubed minus 1. Therefore, you see that 1 is equal to this expression, 1 minus half x squared into x squared plus 1 plus half x into x cubed minus 1. So you have this is f of x now multiplied by a of x and g of x multiplied by b of x. So we see here that one possible choice is that a of x is 1 minus half x squared and b of x is half x. So this is a Bézout identity, which now tells us that that's 1 now. That greatest common divisor is actually a of x times f of x plus b of x times g of x. So it looks like a tedious process, but I think I'm going to take one example in the practice questions to actually drive home the point so we can get an overall picture of this. So in summary, we are saying that for divisibility, g divides f means there exists a quotient q such that f is equal to g times q, That means that a divisor, the dividend f is equal to the divisor g multiplied by a quotient q. So you can use the division algorithm to test this, that f is equal to g q plus r, with the degree of r less than degree of q. Very important. If r is 0, then you say that g divides f. Then we have the idea of GCD. GCD of f comma q is a polynomial that divides both f and g, and any common divisor divides it. So it is unique up to a non-zero constant factor. So we choose the monic one. Okay. Then Euclidean algorithm repeatedly apply polynomial division with decreasing degrees of remainders. So the last non-zero remainder, which is made monic, is GCD of f comma g. Then you have extended algorithm, which gives polynomials a of x and b of x such that GCD of f of g is always equal to a of x, f of x, multiplied by f of x, plus b of x multiplied by g of x. In particular, if GCD of f of g is equal to 1, then we can express 1 as such a combination. As such a combination, this is the polynomial version of Bézout's identity. So let's come to the practice questions, and I'll see if I can pick one question to drive home all the things I've been talking about. Okay, we have to see it in parts. So I'm looking for one problem to take care of. So here we have questions 1 to 8. I'll show 10 and 9 and 10 later. So I'm looking for which one to answer. Hmm. Um, okay, let me go gradually. Want to decide whether x plus 1 divides x cubed plus x squared minus x minus 1. Easy. Just equate x plus 1 to 0. So you have x equals minus 1. So put minus 1 here. So this is minus 1 plus 1. That cancels out. This is minus minus 1. That's plus 1. So, of course, x plus 1 divides because when you put minus 1, everything goes to 0. Decide whether x minus 2 divides this. Factor or use the theorem, the factor theorem. So, of course, if you put 2 here and it gives you 0, and then it means that x minus 2 can divide. Then you can then factor. You can do long division, and you get a cubic expression, which can factor again to get other quotients. Okay? So this one says compute GCD for x cubed minus 4x into x squared minus 4. Now, this is like what we did before, because this will be x into x squared minus 4, which will be x into x minus 2x plus 2, whereas this is x into x minus 2x plus 2. So you can do it just like what we did before. Then use the Euclidean algorithm to compute GCD for x raised to the power 4 minus 1 into x cubed minus 1 over r of x. Factorization can be used to check. You can factorize to check your answer. Of course, that's possible. So, because this video is getting long already, what do I do now? I'm trying to see. Okay, maybe I should go for. I'll just go for question 8, right? It says to compute GCD. Want to compute the GCD for x cubed plus 1 and x squared minus x plus 1. Okay, using Euclidean algorithm, and then use Bézout's identity to write the GCD as. Want to write the GCD as GCD of f of g as a of x, f of x plus b of x, g of x for polynomials ax and b of bx. Okay. Of course, the other two problems, you can now see them 9 and 10. Okay, so let me quickly go for that one and get over with it. So first, compute GCD of this and then use Bézout's identity. So let's go. So it's the same thing we've been doing before, but now I want to do it. I want to attack it from that angle. Like, first of all, compute GCD of x cubed plus 1 and x squared minus x plus 1. That's first thing we want to do. 2, express, or should I say again, GCD, we want to express the GCD as a of x, f of x plus b of x, g of x, following the Bézout's identity. That's basically what we want to do. And what do we do? So the first thing is to find the GCD. So to find the GCD, okay, what do? We divide. So let's say f of x is x cubed plus 1. So I can easily refer to them using their names. Then g of x is x squared minus x plus 1. So the degree here, the degree of f of x is 3, and the degree of g of x, let me say degree f is 3, and degree g is 2. So if so we now say we divide f of x, we divide f of x by g of x. So if anyone with the smaller degree is what you divide with. So, and you have our f of x is x cubed plus 1, right? So that will be x cubed plus 0x squared plus 0x plus 1. Very important. Anything that is missing, you fill it up. Then the other one is x squared minus x plus 1. So let's go now. So x cubed divided by x squared as x times x squared as x cubed, x times minus x, that's minus x squared, x times 1, that's plus x. So then you subtract. So 0. So this is x cubed minus x cubed is 0. Then 0x squared minus x squared. Minus x squared, that is plus x squared. And then 0x minus x, that's minus x. Is that clear? X cubed minus x cubed 0. 0 minus x squared, that's plus x squared. 0 minus x, that's minus x. Then you can drop this one now. So next, we see that we can still divide. So you can then go for this x squared divided by x squared again. That'll be plus 1. Okay. 1 times x squared is x squared. 1 times minus x, that's minus x. 1 times 1 is 1. Okay. So when we subtract this, everything is gone. Everything is 0. Okay. So there's no remainder. There's basically no remainder. So since there's no remainder, we can say so the divisor, so x cubed plus 1, x cubed plus 1 is equal to the divisor, which is x squared minus x plus 1 multiplied by the dividend. The dividend is x plus 1. Okay. So since there are no remainders here now, oh, I didn't know this would be so straightforward. Okay. Since there are no remainders here now, we can simply say then that we can simply say that the GCD, the GCD of x cubed plus 1 and x squared minus x plus 1 is equal to x squared minus x plus 1. Okay, that just takes care of that. So normally we're supposed to get, if we had a remainder here, we'd have also taken the GCD of that remainder with with g of x. But now this is simply what we just have. So now that this is all about it, so we now need to tidy up and see what the expression should really be. Okay. So the GCD. Okay, the second part, which may be a bit tricky since we do have more terms, but let's see. We have x cubed plus 1, okay, equals x squared minus x plus 1 into x plus 1. I should have known this is cubic, right? When we expand, we get that as the second part. So, this is like, mm, so now I think the challenge comes where we need to write all these things. So this is f of x now, and this is g of x. This is g of x plus now this is now you need to tidy things up here. What do we do now? Mm, the divisor is not 1, for instance, but we want to write this is the GCD. Want to write it in terms of all the others. Trying to think about this. So one thing we know is that x cubed plus 1 all over x plus 1 is equal to x squared minus x plus 1, like we've seen already. So that means that f of x all over g of x is equal to x squared minus x plus 1. So clearly they are not co-prime. They are not co-prime. So can we then say that I have a bit of challenge with this. So since the answer is straightforward like this, I wonder how to, and then use Bézout's identity to write the GCD as this. So normally we should start now taking the expressions out, and then we are now able to express that. Okay, I mean, I'll just stop there. because it's so to progress from here is somewhat. But then, I mean, don't forget, you can look at the example we did before. This example, uh, I mean, this particular example we did up to this point, where we now had to we have to keep going back. So we first of all come to this point and make one the subject of formula, knowing that this is g of x, and then again we go for the other one. Here we come here again and make minus 2 of x the subject of formula, paying attention to this. So because we have minus 2 of x here, whatever we get from here, we substitute it into the minus 2 of x here. And then by the time we tied it all up, then we'll have been able to get our a of x, g f of x multiplied by b of x, g of x. So I think I'll just stop this there. It's been a long video already, but that's how that works. Okay. So here now we just have a straightforward common we have a straightforward uh divisor basically. So the GCD will just be x squared minus x plus 1. All right, thank you so much for listening. Don't forget to try your hands on the questions, on the practice questions, and see how well you have understood that. So let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. Okay? Feel free to let me know. And if you have subscribed already, I must thank you very much for doing that. If you haven't subscribed, why not go ahead and do that right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, don't forget to also click on join if you want to become a member of the channel, and that gives you some special privileges. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.